From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'd like to welcome all of you to Optics 505, Diffraction and Interference. It's nice to see so many students out there at 8 o'clock in the morning. And I'll say hello to the students we also have in Seattle and Santa Rosa, California, Boise, Idaho, Raytheon here in Tucson, and in Hawaii, although maybe he's not watching it live in Hawaii this morning. Anyway, this is a course I've taught several times before, and I have to say that I enjoy it very much. I enjoy interference and interferometry. I enjoy diffraction. And part of the goal of this course is to not only make sure that you learn about interference and diffraction, but also to see if I can convince you that it's as much fun as I think it is. There was a handout that everyone here in the classroom should have, and I think everyone out there in TV land, I guess those watching it live don't have it yet today, but you will soon be getting it. And those watching it on tape will probably have the handout by the time you get the tape. So let's look here. That's an outline for the course, and let's go through this. And first we start out with my name and where I'm located here on campus in room 552 in Optical Sciences. Phone number where you can reach me. Well, theoretically you can reach me. You can reach my answering machine in any case. Fax number. And then probably one of the best ways of reaching me is the email address, just jcwyant@u.arizona.edu. And I also have a website that I will, I'm not going to do anything tricky on it, but I will leave copies of notes up there for you if you want to go up there and take down copies of the notes. And I guess maybe the tricky thing about this address is it starts out with W3 as opposed to the www that people normally use. For those of you who watch me out in TV land, I know the address in the NTU information is a little bit different from this, but that address will also work fine. Office hours, I say, call for appointment or see after class. I think the truth of the matter is that whenever you go by my office and the door is open and I'm in there, you're welcome to stop in and see me. So I'm not going to have formal office hours, but if you want to set up a specific time for an appointment, we can do that. Otherwise, just drop in whenever you want. And I guess everyone knows that the class is Tuesday and Thursday from 8 to 9:15, and that you should have had 5:01 or its equivalent someplace. If we go down to the bottom here, I say a little bit about how the grade is determined. And I doubt if there's anyone here who really cares about how you, well, there are a couple of people, I guess, who are interested in how the grade is determined. Well, first off, we're going to have 2 exams during the semester, plus a final exam. And all the exams will be in-class, closed book exams. There's quite a number of homework assignments due, and we'll get to that in future pages here. And since we have I think it was 46 students or so, it's hard to have homework coming in at different times, hard on the graders. And so we're going to be pretty strict. And as I say here, unless special permission is given to hand in the homework late, credit will be reduced 25% for each day a homework assignment is late. And the final grade in the course will be calculated as the homework will count as 20%. The 2 exams will count 20% each, or a total of 40%. And then the final exam will count 40%. Okay? That's pretty much the first page. The second page of this handout goes through the what we're going to cover in the course. And we'll start out this morning with a little 2-minute introduction. And then we'll go on to Maxwell's equations, and we'll spend about 30 seconds there. And then we'll go on to the wave equation. Spend quite a lot of time talking about different waves and superimposing the different waves, and a little bit on polarization. Then we'll go on and talk about basic interference. 2 plane waves, 2 spherical waves, plane waves and spherical waves, plane waves and cylinders, and methods of beam division. And Chapter 5 is one of my favorite chapters here. It's on coherence. Talk about what properties of a source are important in order to be able to get interference. Coherence time, coherence length, theory of partial coherence, fringe visibility, where the fringes localize, correlation interferometry, and so on. And then Chapter 6, we'll talk about classical 2-beam interferometers, plane parallel plate, Fizeau, Michelson, Twyman-Green, Mach-Zehnder, 1,000,001 lateral shear interferometers, radial shear interferometers. All this is 2-beam interference. Chapter 7, we'll go down here and talk about multiple beam interference, Fabre-Perot's neat little thing called a fecal interferometer. That's Chapter 7. Chapter 8, we're going to talk about multi-layer films, a little bit on the theory, and then a little bit about different types of films. Chapter 9, talk about a thing called phase shifting interferometry. And then when we get to Chapter 10, there are 18 chapters here total, I think. Chapter 10, we're going to go on talk about diffraction. First, just a little description of diffraction, and then we'll go through a fair amount of math describing diffraction, Helmholtz equation, Green's theorem, Kirchhoff, Fresnel-Kirchhoff, Rayleigh-Sommerfeld, plane wave spectrum, Babinet's principle. We'll spend a lot of time on Chapter 11. Chapter 12, we talk more about diffraction. In this case, the approximations for Fresnel and for Fraunhofer. And then 13, we'll concentrate on Fresnel, going through Fresnel zones, circular apertures, zone plates, rectangular apertures, large apertures, small apertures, Talbot images, a lot of pretty neat stuff in here. 14, we talk about Fraunhofer diffraction, single slit, double slit, rectangular apertures, circular apertures, multiple slits, diffraction gratings. Again, a lot of kind of neat stuff here. 15, optical transfer function. We'll first talk a little bit about coherent imaging, and then we'll go through the transfer function for incoherent imaging. 16, Gaussian beams, the basic theory, and then what happens to Gaussian beams as they propagate through optical systems. Then Chapter 17, holography. Explain physically what holograms are, and we'll go through a little math showing what holograms are. We will talk about thin holograms and thick volume holograms. We'll talk about applications. Chapter 18, speckle. What is speckle? What causes speckle? How do you get rid of speckle? You can't, so let's use it for something. So we'll talk about applications. So that's the outline for the course. I saw a sign on the door that food and drinks are not allowed. So this may look like coffee, but it's actually medicine that I have to take in the morning. Otherwise, I will lose my voice for sure. So that's an outline for what we're going to cover. It's a lot of material. It's fun material, and I think you will enjoy it as much as I enjoy it. In order to cover this much material, we have to make sure we stay on schedule. So the next part of the handout here shows you the schedule, and I'm sure we won't stay exactly on schedule, but we'll be reasonably close. And so today is what, January 15th? We're going to cover sections 1, maybe I should say Chapter 1, Chapter 2, and we'll start Chapter 3. Next week, we'll spend both Tuesday and Thursday on Chapter 3. And then we come to the 27th of January, and there's going to be homework due. And there's going to be 3 homework problems due. And in a minute, I'll explain what I mean here by WP1 and WP4 and WP8 and so on, so you know what the homework is. So if we look down the list here, we don't need to go through the whole schedule, but if we look down the list, you see typically you have 3 homework problems due a week. And they're not going to be real difficult. They're hopefully not going to take a lot of time. But it is important that you do the homework problems for a couple of reasons. One is it counts as, 20% of the course. Well, what I think is more important is that as you do the homework problems, you will learn the material. And without doing the homework problems, it's going to be very hard to learn the material. And as you'll see in a little bit, I'm going to give you a lot more, a whole list of problems that you can do. These are the only ones that are assigned, but if, the interested student will probably work more problems than what's assigned, right? Okay. Everyone's shaking their head yes, or yeah, almost everyone. So anyway, we go along here and we see all these homework problems, and then we come down here to February 26th, and it says test on sections 1 through 7. So that's on February 26th, and then we go down here, keep going, and we come to April 9th, and we see a second test on sections 8 through 13. And then we come down here to May 5th, and that's the last class. And then someplace down here, the university will tell us when there will be a final exam. Okay. So any questions on the schedule here? Okay. Well, there's a little more to the handout. And the last part of the handout is a list of books. And I have what I call primary books, and I have what I call secondary books. And I think that technically you're not required to buy any books, but I will strongly recommend that either you have the primary books or you have a friend who has the primary books, because they will prove pretty useful. So 3 primary books. The first one is what we often call the Bible of Optics. It's Principle of Optics by Born and Wolf. Does everyone have a copy of Born and Wolf? I strongly recommend this book. The book is old. I mean, I was thinking the other day that this book was first published when I first started high school, and so you would think it's greatly out of date. But I think probably the book has aged better than I have aged. And I guess if you look at principles of optics, they don't change. And so even though this book was first published sometime in the late 50s, it still is very current. There's a new edition now, and I'm not even sure what the edition number is. Can anyone tell me? Okay, don't know. What? 7? Brand new. 7. But it hasn't. The last several editions have not changed very much, and so it's not really required that you have the latest edition. But everyone in optics should have a copy of Principles of Optics. I mean, everything is there. And I keep forgetting that. I'll be trying to find something, and I'll look all kinds of places, and I can't find it, and then finally I remember, I should go back and look in Born and Wolf. And of course, it's there. So, it's a great book. Second book is one of Goodman's book, Joe Goodman. It's an Introduction to Fourier Optics. It's an absolutely superb book, extremely well written. It's a masterpiece. The first edition was published maybe 1968 or something like that, and then a new edition came out maybe 3 years ago. And I think this is a case where, I mean, the first edition was superb, but the second edition is even more superb. And so I think this is a case where you should have the second edition. And we will not use this until we get to diffraction, but once we get to diffraction, we will use it a lot. And it's so well written. It's just superb. The third book on the list is Heck's book on optics. And a new edition of that just came out. I think the first edition was published about 1974. And the authors were Heck and Zajac. And in about 1988, they came out with a new edition. And I never quite understood why one of the authors disappeared, because that was by far the biggest change in that edition, was subtraction of one author. And now a new edition has just come out, and since I'm using it for the course, I thought I probably should buy the latest edition. So I went over and found out the price is something like $85. And I bought it. And I have to say there's not a lot of changes between the second and the third edition, and there's not a lot of changes between the first and second edition. So I don't think it's important which edition you have. But the book is a good book. And basically and I think everyone in optics should have a copy of it. And basically what they have done is they went to Born and Wolf. And those of you who looked at Born and Wolf, you know what, everything is there, but sometimes it's a little difficult to understand. And so what Heck did was he went to Born and Wolf, and he took out probably the most important part and rewrote it in a way that people can actually understand it. And so if you read Heck's book, you'll understand the basic principles, and then you'll go back to Born and Wolf, and you can find out more details. But Heck's a pretty good book, but I don't think it matters which edition you have. Then I list a whole bunch of secondary references, and let me spend a little time going through these. And these are not references that I think you should go out and spend your money on, but they're kind of, every now and then they're interesting to look at. The first one is several authors here, Waves and Optic Simulations. And I added this book, I guess, last year to my list. And the thing I liked about it was it had some software in it that gave you little simulations of interference and diffraction as well as other things. And the software is in DOS. And I absolutely hate DOS. I never liked DOS. Before Windows 95, I was a Macintosh guy. And I always refused to even allow DOS software on my computer. But this was good enough that it was the only DOS software I allowed in my computer. And I thought I would demo it this year in class, since we have a nice hookup here to the computer. But now, for the life of me, I cannot get it to run under Windows 95. It just will not run on my computer. And I have a Windows NT computer, too. And on that, sometimes it runs, and sometimes it doesn't run. So I don't know. I don't think I'm going to use it for simulations, because I think I just can't get it to work for some reason. I don't know why. Okay. Other than the simulations, the rest of the book, I wouldn't buy it for the rest of the book, I guess. Optical holography. We talked a little bit about holography, and kind of the best book over the years is Collier, Burkhart, and Lynn. Good book. You don't really need it for this course, but interesting book. Laser speckle. At the end of the course, we talked about laser speckle, and Dainty's book is a pretty good book in that area. Next one is Light by Ditchburn. It's an old book. I don't know if you can buy it anymore. It has a lot of material in it. It's sort of like, Born and Wolf. When you can't find it anyplace else, you look in Born and Wolf or you look in Ditchburn, and it's probably there. It's pretty good. Fransone has a number of books. Optical Interferometry. It's not one of his better books, but I have it on the list. He has a book with Malik on polarization interferometers. That's, in my opinion, a very good book. We're not going to use it much in this course, but it's a very good book. Fransone and others have a 2-volume on pretty pictures, Atlas of Optical Phenomena. Very pretty pictures in these books. I think Optical Sciences has the first edition, and I guess I have a copy of the second edition, which at some point I'll bring here so you can at least look at it. I don't think it's in the library, and I don't think you can buy them anymore. Goodman has a second book on statistical optics, and everything Goodman does is fantastic. So, I mean, that's a fantastic book, too. But we won't cover much in this course on it. Heron, a couple books on interferometry and on holography. I'm not crazy about his first interferometry book. His holography book is superb. The basics of interferometry is pretty good, but it's kind of low level. An old book, probably should take off the list, but back when I was a kid, it was a great book, Jenkins and White, Fundamental of Optics. It's sort of, it's an old version of Heck's book, and nowadays I would use Heck instead of Jenkins and White. Jones and Wykes on holographic and speckle interferometry, interesting, but don't need it too much for this course. Klein's book on optics, a lot of good books on general optics, and I don't know, Klein is an interesting book, although I always had the feeling that he always explained things in the most difficult way possible, but in any case, not a bad book. Mertz's book on transformations in optics. Mertz is a clever guy, really, really clever guy. And there's a lot of really good stuff in this book. Mertz is not a good writer, and you almost have to know the material before you can understand it from the book. But I would not use this book for this course, but hopefully after this course you'll be able to go to Mertz's book and understand some of what he's saying. He's a very, very clever guy. He used to write books and articles in JOSA, and articles were superb technically. From an English viewpoint, they lacked a little bit. They kept being rejected. Mertz being a clever guy, in those days they had ads in JOSA, so he took out ads, and that's where he published his papers. And I mean, it's a great collection. I have pretty much a whole collection in my office. It's a lot of clever things. He's a very clever guy. Moeller's book in optics, it's another good optics book, but we won't use it for this course. The Physical Optics Notebook by Thompson and others. Again, it's a good book. I mean, nowadays there's so many good books out there. It's amazing. Soleil and Tisch has what is basically a handbook called Fundamentals of Photonics. Previous years I've used a portion of that when I talked about Gaussian beams. I may or may not use that this year. But it's basically a kind of a handbook, I guess I would say. Scott's book. This is a new book. In fact, its publishing date is 1998, although I got it in December of 97. And, I don't know, maybe 6 months ago, I got a phone call from someone, well, from Scott, actually, saying he was writing a book, or he had written a book, and he was just publishing it, and he needed a picture for the cover of the book. I wanted to know if I had any pictures. And I said, I have millions of beautiful color pictures. He said, well, he didn't want a color picture, he wanted a black and white picture. So I found what I thought was a nice picture of scatter plate interferometer interferograms. And probably don't know what a scatter plate is, but as time goes along you will. So anyway, I sent that in, and so now when you look at Scott's book, you see my picture on the cover. So I got a free copy of the book. So I said, well, it's pretty good. So I'll look at it. It's actually a pretty good book. There's a nice section in there on plane wave spectrum, which we will talk about when we get to diffraction. And it's a very good book, I would say. I'm happy with it. Steele's book on interferometry. There are 2 editions of this. The second edition is the one I would recommend. Very good book. Stone's book, Radiation and Optics. This is an old book. It's a book that I used when I was a senior in college, and so I keep it on the list. But it has some nice stuff in it on Fresnel diffraction. I like very much. When we talk about Fresnel diffraction of circular apertures, we'll use some material from Stone's book. Talansky on multiple beam interferometry. Talansky was the real leader in multiple beam interferometry. Good book, but everything we cover in multiple beam in this course comes out of Warren and Wolf. Then my last book on the list is Vest's book, Holographic Interferometry. Vest was a mechanical engineer who went on and who is now the president of MIT. But he got into holography from the mechanical engineering area. And it's a superb book on holographic interferometry. If you ever get involved in holographic interferometry, this is the book to look at. He's very good at explaining things in nice, simple ways, and superb book. Anyway, that's my list of books. And as I said, it's the first three that you should concentrate on, but the other books are interesting to look at, certainly. And I need a little more of my medicine. So any questions before we start here? Okay, well, Chapter 1 is entitled Introduction to the Theory of Interferometry and Diffraction. And we're going to give a kind of a 2-minute introduction here. I mean, interferometry is kind of neat in that if you take two beams of light, and if these two beams of light have a property that we'll call coherence, we'll describe in this course what we mean by coherence. But if these two beams of light are coherent with respect to each other, when we combine these two beams of light, what we will see is that in some cases the resulting irradiance is greater than the sum of the irradiance of the two beams. And in other cases it's less than the sum. And in fact, in some cases it may go to 0. If we integrate over all space, of course, energy has to be conserved. But this thing that's going to be called interference is a way of changing the distribution of the irradiance of the energy. And we get these things that we call interference fringes. And as we go through this course, we're going to worry about the shape of the fringes and what determines the shape of the fringes. We're going to worry about the contrast of the fringes and what properties of the beam determines what the contrast is going to be. And we're going to worry about different ways of putting these two beams together, and we're going to see that there are two fundamental ways. One is called division of wavefront, which will work well with small sources, and the other is going to be what we call division of amplitude, which will work with small sources or with extended sources, either one. Now, a lot of the course, first half when we talk about interference, a lot of that will be talking about two-beam interference. But as we go along, there will be a period of time when we'll talk about multiple beam interference. And we'll even let the limit go to infinity, so we have an infinite number of beams interfering. Historically, interference has been very important in optics. Interferometry has a lot of applications in spectroscopy, in metrology. And I always like to say, you can measure things as small as millionths of an inch or smaller than that. It's incredible. Fractions of angstroms you can measure. Or if we go to stellar interferometry, we measure things that are millions of miles apart. So it's a wide dynamic range. I'll write down a couple of names. There have been a lot of people who worked in interference and interferometry over the years, but let's write down a couple of names here. And the first thing is that if we go back to the 1600s, people began to talk about something that's now called Newton's rings. And you don't need to really write this down. Now, we're going to talk more about Newton's rings, and you probably want to hear later in the course, not today. And these, if you go back, you'll see that there are actually two people who discovered these. There are two people who get credit for discovering it. One is Robert Boyle, I should say. And that's 1627 to 1691. And the third one is Hooke, again another Robert, and that's 1635 to 1703. And I like writing down these dates because the point I'm trying to get, one point I'm trying to get across is that when we talk about interference and we talk about diffraction, I mean, this stuff has been around a long time. It's not new, but it still is very, very important today. And if we go, so this is back in the 1600s. If we go to like 1801 or sometime like that, we have Thomas Young. Who really was able to explain interference, the principles of interference. He was able to explain, well, you look at thin films, you see various colors. He was able to explain the colors of thin films. So this is, 1800 or so. If we go along to the guy who I think in the area of interferometry was really is the god of interferometry, I would say it's Michelson. And we'll talk about several of his interferometers in this course, but he lived in 1852 to 1931, I guess it was. And he was probably most famous for not being able to see the ether drift. And this was later resolved by Einstein in his special theory of relativity. I mean, if you go back and look at Michelson papers and books, he knew everything there was to know about interferometry. This is a long time ago. So that's interferometry. Now, if we go to diffraction here, probably Da Vinci is a guy who's maybe was one of the first people. At least he gets credit for being one of the first people in diffraction. And get some dates here. This is 1452, 1519. Probably the first book on diffraction was a man by the name of Grimaldi, 1665. Again, I mean, old stuff, but diffraction interference has certainly been around a long time. Fresnel, his name is going to come up in this course a lot. And I put a date down here of 1818. He really put a good foundation on diffraction using Huygens wavelets and really combined it with interference. And then the guy who really added the math to this to explain it well is Kirchhoff. And so that's 1882. And so he did a good mathematical analysis of diffraction. So this material, much of the material we're covering in this course is very fundamental material, and it's been around a long time. There have been lots of people who have sort of extended the work sense here. A lot of writings on this material. If we kind of look at the course is diffraction and interference. So you might say, what's the difference between diffraction and interference? And the answer is going to be not very much, actually. They're very, very similar. And kind of the way that I think about it is that in interference, we're combining a discrete number of beams. Maybe it's 2 beams we're interfering, 3, 5, 10, or multiple beam interference. It may actually be an infinite number of beams that we're interfering, but they're all discrete beams. In diffraction, it's a continuum of beams. And so basically, we take interference where we have a bunch of summation signs, and we go to diffraction, we replace these summation signs with integrals, and that's it. So the two are very, very similar. And I guess in this section, I have one more little, I realized something else I forgot to cover, but one more little thing here. I'll cover it now. If you go up to my website, you're going to find a few documents up there, or if you go to Optical Sciences, you're going to find, and go into the library, you're going to find a notebook in there. It says Optics 505 in it, and there are some additional notes in that. And one set of additional notes in there will be a set of view graphs on interferometry. And the first part of this view graph is where I just kind of summarize a few words about interferometry. where it says, interferometry has hundreds of uses and is one of the most powerful tools of science. You can measure distances as small as a fraction of a millionth of an inch to as large as millions of miles. And I go on to say basic interferometry techniques are old. However, at the present time, the interest is greater than ever. And why is interest greater? Well, it's great because we can combine these classical techniques with electronics and computers. Anyway, this is the first part of a set of view graphs that you might want to have a copy of. And mainly because in these view graphs I have a lot of pictures. And I don't like drawing pictures in class for two reasons. First, it takes time. And the second is, well, if you saw me draw some pictures, you'd know you don't want me to draw them either because I'm not a very good artist, okay? And so these view graphs have pictures that you can actually look at and sort of tell what they are. And so it's handy to have. The other thing that is in these notes, both up on my website and in the Optical Sciences Library, is the homework problem sets. And that's what I really forgot to mention before. In the outline, I refer to, I don't know, WP1 and WP3 and such, What are these problems? Well, what I've done is I've put together a set of problems here, many pages thick. It's a list of problems that I've given as homework over the years as I've taught this course, or a list of problems that I've given as exam questions. And so your homework comes out of here, and I refer to WP1. Well, that's the question you're supposed to answer. WP3, so on. And so the way you can get these homework sets here and the other notes are A, you could go to the website, get them there if you want to. B, you can go to the Optical Sciences Library, and you'll find them in a notebook there. And C, I'll ask you a question. Do you want me to have these Xerox someplace so you can pick them up? Okay. And do you have a place in mind in particular? I will find an appropriate place and put up a notice later today. And so I will take both the homework assignments there and these view graphs there. So you can pick them up that way if you want to. Okay. Well, that was my little introduction. Any questions before we go on and go to Maxwell's equations, I guess? That's next on the list. Okay. The advantage of getting some of these notes off the website is, if you want, is that they're in color. And I don't know if you like color or not. But, well, the homework problems aren't in color, but the view graphs are in color. Yep. And what's up on the website is I have printed out in PDF files, Adobe PDF files, and I don't know how many of you know about that. It's a great way. You just print it out, and it looks just like this. And you can get a free Adobe reader, and I give a link from my website to that reader. And I find that is a very, very convenient way. So you have it on your computer. You can print it out, any printer, and it actually will look like this. So you don't need to have Word or PowerPoint or whatever. You can use a free Adobe reader. How many of you have used PDF files in the past? Okay. Well, I love them. But I should also admit I also own some stock in Adobe, so maybe I'm a little partial towards it. Okay, Chapter 2, Maxwell's Equations. I kind of feel every course in optics should start with Maxwell's equations. And so we will do that. And we'll spend a good 2 minutes on them. So, and I'll do it in red. Okay, so this is Chapter 2.0, Maxwell's Equations. And we're going to do them in empty space. So, tough question for you. How many Maxwell equations are there? 4. Oh, I was worried for a second. Didn't know. Well, you have what the curl equations. So del cross E is minus what mu naught partial H respect to T. I shouldn't even have to say what E and H are. Okay. Electric field, magnetic field. Del cross H is epsilon naught partial of E respect to T. So these are the curl equations. Okay. Then we have the divergence equations. Del dot E is equal to 0, empty space. Del dot H is equal to 0. So these are divergence equations. Okay. That's the end of chapter 2. Yes. Yes, So anyway, that's the end of Maxwell's equations. We now go on to chapter 3. Okay. I told you we weren't going to spend a lot of time on Maxwell's equations. Well, what we're going to do now is going to write down their wave equation. And those of you who have done this before, and I assume everyone has derived the wave equation before, but we should do it here. We're going to start out with this vector identity. And which is going to be that del cross E is equal to del times del dot E minus del squared of E. And del dot E from Maxwell's equations is equal to 0. And so this is minus del squared E. And so what we have here is that minus del squared E is minus mu naught del cross partial of H with respect to T. Again, we get that from Maxwell's equations. And so we could make this as minus mu naught partial with respect to T of del cross H. And where the order of time and space differentiation can be interchanged if H is sufficiently well behaved. And so we can write this here as what? Minus, again from Maxwell's equation, minus mu naught epsilon naught second derivative E with respect to T. And so what we have down here is that del squared E minus mu naught epsilon naught second derivative E with respect to T is equal to 0. Draw a box around that. And then we will define C, velocity of light, as the square root of 1 divided by mu naught epsilon naught. And so what we have here, go to the next page, and I'll put the page the other way, it might work a little bit better, is that we have that del squared E minus 1 over C squared, second derivative E, respect to T, is equal to 0, and we'll call that the wave equation. I'll get fancy here and draw a box around that in blue. So that's our wave equation, and we could do a similar equation for H if we wanted to. And all of you have seen this many times in the past, and you'll see it many times in the future. The next thing we might do is to just look at the one-dimensional case. And so the one-dimensional wave equation. And that's the second derivative of E, respect to T, respect to X, let's make it, excuse me, respect to X, minus 1 over C squared, second derivative with respect to T is equal to 0. So we'll just write it for one dimension here. Okay, so that's the wave equation. And so what we want to do now is to find solutions to this wave equation. And then once we find these solutions, find these waves, then what we do in this whole class is play with these waves. Okay? I'll take a little more of my medicine here. So this takes us to section 3.1, which is going to be solutions to the wave equation. Solutions to wave equation. And what we're going to talk about here will be transverse waves. So maybe the best way to find a solution here is that we just write down a possible solution. And I might cheat and look in a book or something. Write down a possible solution, and then we'll see if it actually works. And one possible solution here is that E, as a function of distance and time, so one dimension here, is equal to some E naught times a cosine of kx minus omega t. Possible solution. And so if I were to plot this as a function of x, I would have some cosine function. Okay. Now, if we want to determine if that's a solution or not, what we're going to do is take this and plug it in to our one-dimensional wave equation and see what happens. Let's move that up to the top here. And so if we plug that in to our wave equation, we will get, I have to take a second derivative with respect to x, and so I'm going to get a minus E naught k squared cosine kx minus omega t. And then we need to take minus 1 over c squared, the second derivative with respect to t. And so that's going to give me a plus omega squared over c squared E naught cosine kx minus omega t equals 0. And so this will be a solution. This works out fine if k is equal to omega over c. Then it's a solution. Or sometimes you see this at c is omega over k. So as long as that we have this condition right here, then this will be a solution to the wave equation. And the other thing that we often do is we let k, whatever k is, be equal to 2 pi divided by lambda, which is what we will know as the wavelength. Okay? So this is a solution to the wave equation, and it was really the one-dimensional wave equation, and so that worked pretty well. Well, let's go on here and not just worry about one dimensions. Let's worry about the three-dimensional case. And so This will take us to section 3.2, which is entitled Plane Waves. And so just writing down the three-dimensional wave equation again here. Del squared E minus 1 over C squared, second derivative of E with respect to T is equal to 0. And one solution here that we can find, and it just goes back to what we did for the one-dimensional case, is that E of now x, y, z, as well as time, t, is equal to E naught cosine k dot r, we'll worry about k and r are in a second, minus omega t. And r here is going to be x unit vector in the x direction plus y unit vector in the y direction plus z unit vector in the z direction. And we're going to call this r here, we're going to call that the position vector. Okay? And k, this other guy in here, and r is a vector, I should make that. K here is equal to something in case of x, x direction, plus k sub y in the y direction, plus k sub z in the z direction. And this is what we're going to call the propagation vector. Okay. And, I mean, it gives the direction of propagation. So now what we want to look at, this k dot r minus omega t, look at that for a second here. So we'll move this up to the top. So k dot r minus omega t. So that's equal to k sub x times x plus k sub y times y plus k sub z times z minus omega t. And for this being a constant value here, this is equal to a constant. And if we look at this, what does this represent? Well, this represents a plane. So this represents a plane in space of constant phase. And therefore, what do we call this? We call it a plane wave. Okay? So that's our definition of a plane wave. We'll deal a lot with plane waves during this course. So that's section 3.2. Change color. Go to section 3.3. I don't know, 3.3 is a section I probably shouldn't even include, but I will. Just call it complex representation. And everyone knows this, but I'll write it down anyway. We all know that e to the iu is cosine u plus I sine u. If we have something, a wave, e of x and t, that we write it as e naught cosine k dot r minus omega t. So that might be e of x, y, and z, maybe I should say. that we can write this, to make life simple for us, we can write this, the E of x, y, z, and t is equal to E naught, e to the I, k dot r, minus omega t. So we can write this in complex notation if we want to. But we have to remember that physically what matters is the real part of this. But we like to use, often we'll use this in the complex notation just because the algebra is simpler. But the thing to remember is that the physical reasons, the real part is a quantity that we're interested in. So actually, only interested in real part. Okay? But we'll use complex notation to simplify the work. Okay, so that's it for chapter 3, section 3.3. So let's put that off to the side. And we'll go to section 3.4. And 3.4 is called spherical waves. And if we just say, well, cosine of kr minus omega t, or if you like, e to the I, kr minus omega t, you might say, well, these have constant values on a sphere. So you might think that they are represent spherical waves. But if we take these and plug it back into the wave equation, we'll see that these are not solutions to the wave equation. And in order to get solutions to the wave equation, and I think you'll see this in one of your homework problems, we have to make a 1 over r here. There has to be a 1 over r cosine, a 1 over r e to the I. And then this will represent spherical waves propagating out from some point. And the r simply comes in because as a wave becomes larger, the amplitude is going to go down. And it's going to go down as 1 over r. So anyway, as I said, I think you'll have a chance in a homework problem to show that this is that these are solutions to the wave equation. Okay? So that's section 3.4. So we're going along pretty well. We've covered chapters 1, chapters 2, and all the way through section 3.4. So maybe this course will be done by February or so. I don't know. Well, maybe we'll slow down a little bit. I don't know. We'll see what happens. That reminds me, basketball. I love basketball. I don't know. You people like basketball? Of course, yeah. Horse. Yeah. Okay. How many of you go to the basketball games? Yeah. 2 A's and back. Any other? Yeah, it's not going to be good grades, I guess. Okay. Anyway, speaking of basketball, I'll now begin writing in green ink. I think that's more appropriate thinking about basketball. Okay, 3.5. Linear superposition. You see that green okay? Okay. Well, in this course, whether we're talking about interference or diffraction, we're going to have generally a lot of beams, a lot of electric fields. And what we want to say is that the resultant electric field is equal to the sum of the individual electric fields. So E is E1 plus E2 plus E3 plus so on. And the first thing we note here is that we're writing these as vectors because the electric field has some direction. And so when we add the electric fields, we have to add the electric fields as vectors. The next thing is that this, I like just writing it out this way, E1 plus E2 plus E3. And that's very good if we have no matter present. But if we have matter present, and if the electric fields become large, we get into something called nonlinear optics. It no longer adds as nicely as this. But we're not going to cover nonlinear optics in this course. We're going to assume that either we're in a vacuum, or we will assume that the electric field is small enough that we don't have to worry about nonlinear effects. And we're going to assume that we can write the electric field as this throughout the whole course. Okay? So now what we're going to do is we're going to look at combining different electric fields. And the first is section 3.5.1. And what we're going to do here is that we're going to take two sine waves. Well, we're going to take, I'll just say sine waves first off. And they're going to have the same frequency. So two sine waves having same frequency but different amplitude and phase. Okay? So move that up to the top. And under here, the first section is 3.5.1.1. You're soon going to learn I love numbers like this. So anyway, we'll first just talk about two sine waves. Okay. And for the time being, let's say both these sine waves have the same polarization. So we'll say same polarization. So I don't have to worry about these vectors. And the first sine wave, we will write here, E1 of x and t is A1 cosine kx minus omega t plus phi 1. And if you want, you could write that as the real part of A1 e to the I phi 1 e to the I kx minus omega t. Now normally when we write things in complex notation, we won't bother to write down real part because everyone here already remembers that it's the real part that we're going to work with. So that's one sine wave. It's a kx minus omega t for phase plus some initial phase at phi 1. Now second sine wave, we will write here the E2 of x and t is A2, different amplitude, cosine kx minus omega t, same frequency, but a different phase, phi 2. Okay? And I could do the real part there if I wanted to, but well, I might as well. One more time, one last time. Real part, A2, e to the I, phi 2, e to the I, kx minus omega t. Okay. So now if I want to write down, I'm going to add up these two. Write down some, I guess I call it E0 of x and t. E1, so it's equal to E1 of x and t plus E2 of x and t. And so, and I'm not going to write down this real thing anymore. You all know that. I'll just write that down there. I'm just going to add these two guys here. And so that's what? A1 e to the I phi 1 plus A2 e to the I phi 2 times, well, we had this common thing in both of them, of e to the I kx minus omega t, and that's it. So that's the sum. A1 e to the I phi 1 plus A2 e to the I phi 2 times e to the I kx minus omega t. And so we could rewrite that, or write that here as, I don't know, this is some complex number, which I can write as A naught e to the I phi naught, and then I have e to the I kx minus omega t. So that's kind of interesting. So what happened here when we superimpose these two sine waves of the same frequency? What we got was another sine wave of the same frequency, but a different amplitude and a different phase. So superposition of two sine waves of given frequency produces a sine wave of same frequency with some given amplitude and phase. Simple, but rather important. And I'll show a little picture here. And I'll bring you a Xerox copy of this picture next class, but you can also get it off the website if you want to, and you can get it in real color if you want to. But what we're saying here is that I have two sine waves. I have this green guy, cosine of x, and then I have this blue guy, which has a different amplitude, A, and a different phase, alpha, in here. So it's A cosine of x plus alpha. And we simply add these two, the green and the blue, and in this case we get the red. So we get a sine wave, same frequency, but a different amplitude and a different phase. Okay. So now what we want to do is to go back here and calculate this amplitude and this phase. And I think we have enough time here to do it. So let's do that. So we go back here, and so we're just going to go back and say, well, this here is equal to this. And so we would have that A1 e to the I phi 1 plus A2 e to the I phi 2 is equal to A naught e to the I phi naught. I mean, that's what we said here. We just set these equal. So now I have to do a little algebra here, and we can write that A1 cosine of phi 1 plus A2 cosine of phi 2 plus the imaginary part I times A1 sine phi 1 plus A2 sine phi 2 is equal to A naught cosine phi naught plus I A naught sine phi naught. Okay? And now we just set the real parts equal, and we set the imaginary parts equal. And we're going to take the ratio of imaginary to real. So we have A naught sine phi naught is equal to A1 sine phi 1 plus A2 sine phi 2. And we have that A naught cosine phi naught, setting the real parts equal, is equal to A1 cosine phi 1 plus A2 cosine phi 2. And we'll do a division here then. Real parts are equal, imaginary parts are equal. And that's equal to the tangent phi naught. E naughts cancel. So the tangent of the phase of the resultant beam is equal to A1 sine phi 1 plus A2 sine phi 2 divided by A1 cosine phi 1 plus A2 cosine phi 2. Okay. So that gives us the phase of the resultant. Now let's look at we want to find the amplitude here. So let's square both sides here. And so we have A naught e to the I phi naught, which we'll square. So that's just A naught squared. So that's going to be equal to this squared. So that's A1 e to the I phi 1 plus A2 e to the I phi 2 squared. And so we just square this here. We have A naught squared is equal to, well, what that's going to be A1 squared, A2 squared, plus, we're going to get A1, A2 times e to the I phi 1, e to the minus I phi 2, and then we're going to get the complex conjugate of that. And so when we do all that, that's going to become 2 A1, A2 cosine of phi 2 minus phi 1. I'll draw a big red box around that. Put it up here. So this is saying that what we have is the amplitude squared is the amplitude of one squared plus the amplitude of the other one squared plus this interesting interference term that will turn out, 2A1, A2 cosine of the phase difference between the two beams. And to be truthful, I mean, this is all there is to two-beam interferometry. So we could almost take the rest of the first half of the semester off. This is it. Okay? Maybe I'll be able to think of something else to think about, talk about. But that's basically it. That's two-beam interference. So, I think you should dream about this nights, between now and next class. One other thing we can write here that's kind of interesting. What was that about dreaming? Oh, okay, can we go back there? Right there. And so there's one other thing that's of interest here, and that is if, for example, A1 is equal to A2, then you would have that A naught squared is equal to 2A1 squared times 1 plus cosine phi 2 minus phi 1. And if you want to go to your trig identities, you can rewrite that as 4A1 squared cosine squared of 1/2 phi 2 minus phi 1. So these, what we're going to call interference fringes, we get, you can think of them as cosine fringes, or you can think of them as cosine squared fringes. It's really equivalent. So anyway, this is very important result here. We'll see it lots of times this semester. What we're going to do next class, we're going to start out here and not just have two sine waves, but we're going to combine several sine waves and see what happens in that situation. And then we will go on here and look at different frequencies, looking at beams going in different directions and so on. So anyway, that concludes our first class here, and I'll see you bright and early, next Tuesday morning. Thank you very much.